Okay, so this is section 17.4, solubility equilibria. So we're going to do an introduction into a particular type of equilibrium constant. If you recall, some ionic compounds are very soluble in water. They dissolve in water very well. For example, if you take a sodium ion and combine it with a chloride ion to form sodium chloride, and then dissolve that into water, what you'll find is the two ions will separate and become hydrated by the water molecules, right? So we have aqueous sodium ion and aqueous chloride ion. Very soluble. But you may also recall that there are some compounds that don't dissolve in water. So some ionic compounds are what we call insoluble in water. An example of that is silver chloride, AgCl. If you take silver chloride and you try to dissolve it into water, what you'll find is it just essentially doesn't dissolve. It just will fall down to the bottom as a precipitate. Now, if you study the solution, or you study the mixture of sodium chloride dissolved in water, you'll find that it's not exactly the whole story. It turns out a tiny bit of it will dissolve, a small fraction of a percent. And so I'm going to write it like this. Just like I did for the sodium chloride. However, I'm going to point out that if you take the sodium ion and combine that with the chloride ion in water, the reaction will go pretty far to close to completion. In other words, over 99% of the sodium ions will combine with over 99% of the chloride ions to form silver chloride. So that's the reverse of what we just saw there. So for convenience, what we do is we say that both of these reactions are possible, so we call it a reversible reaction. And we apply all of our understanding of chemical equilibria to this situation. Okay? So this is the equilibrium expression, or the equilibrium equation for the issue of what we call solubility, the dissolving of substances that are not all that soluble in water. And so just like with any equilibria, we have associated with this an equilibrium constant. And we call it KSP, where the S stands for solubility and the P stands for product, solubility product. So when you hear or read the word solubility product, in your mind you want to think immediately equilibrium constant, a K. Okay? Now, if you recall, for heterogeneous equilibria, we do not include liquids or solids in our expressions for equilibrium constants. So what we have here is silver concentration times chloride concentration. And so it's called the solubility product. It is the product of just the products, right? There's no reactants in this equation. Now, suppose we have another more complicated chemical formula. So here's one that's pretty complicated. This is calcium phosphate. Calcium phosphate does not dissolve very well into water, but when it does, you get 3 calcium ions and 2 phosphates. Right? Again, we're going to use the double arrow to indicate that this reaction can go either way. It's equilibrium. So the expression for this particular reaction would be the concentration of calcium to the third power, right? There's a 3 as a coefficient, times the concentration of phosphate to the second power, where that second power is coming because there's a 2 there, okay? So that's writing the expression for the solubility product. Now what I'd like to do is I'd like to show you some values taken from your textbook at 25 degrees C. So maybe we could find these. This silver's not in this list because I only went up to the alphabet, went up to M. But calcium might be in there, calcium phosphate. If you look down 2, 4, 6, 8, 10, the 10th one from the top, calcium phosphate is shown. The equation, the chemical equation is shown, and the value of the KSP is shown as 1.2 times 10 to the minus 26. So they can be very small values. In fact, if you look at the one way up at the top, aluminum hydroxide, that is a really small equilibrium constant, 10 to the negative 33, tiny, tiny. In fact, bismuth sulfide, which is the 5th one from the top, 1.6 times 10 to the negative 72. Tiny values, small equilibrium constants, okay? So that's a little intro into the solubility product. The rest of this is really just figuring out how to do certain types of calculations. So the first one that I'm going to show you, these are very standard type problems that we'll look at. The first one is we're going to know the value of KSP, and then from that we're going to find the solubility of the salt. Okay, so the example I'm going to show you is silver bromide. So silver bromide, AgBr, it's like silver chloride, not very soluble in water. So you get silver ion and bromide. Okay, and the KSP is, I'm getting that from the table, it's 7.7 times 10 to the minus 13. And that would be equal to the concentration of silver ions times bromide ions, right? That's the product. Okay, so the first question we're going to look at is given KSP, meaning we know the value of KSP, find the molar solubility for the salt. And the molar solubility is defined as the moles of the compound that divides into 1 liter of solution. So if I have 1 liter of solution, how many moles of silver bromide would dissolve into that 1 liter? Okay? That's called the molar solubility. Now, here's how we're going to go about this. We don't have any initial concentrations like we've had in previous types of equilibrium problems. We just have the value of K. But it turns out because only the products are in the expression for K, these types of problems are really straightforward. So here's what we do. A silver bromide is a solid, so we're not even going to worry about silver bromide in terms of doing any calculations with it. What we're going to focus on are the products because those can dissolve into water. So initially, before any of it dissolves, so imagine that you take the salt out of a salt shaker and you start sprinkling it into the water and you're trying to see how much of it dissolves. What you would do is you would say the moment they contact the water, none of them have dissolved. The silver bromide is just in solid form. So the concentration of silver ions, Ag+, and the concentration of bromide ions, Br-, would be 0. That's the initial concentrations. But if you do a Q calculation, reaction quotient, Q is going to be 0. So that means that Q is less than K, and that means the reaction proceeds toward the product side. So what we get is plus X. Actually, your textbook, I'm going to go ahead and try to be as consistent with your textbook on here as I can. Your textbook uses the symbol S for solubility. Okay, so I'll go ahead and use that as well. And the same would be true for the bromide. So at equilibrium, 0 plus S is S. 0 plus S is S. So at equilibrium, the concentration of silver is S, and the concentration of bromide ion is S, which means that KSP is equal to S squared, right? And we already know what the value of KSP is. That's given. 7.7 times 10 to the negative 13. So what do? The next step is just to find out what S is. So S is the square root of 7.7 times 10 to the minus 13. So I'm going to go ahead and calculate that. (7.7) times 10 to the minus 13. Take the square root of that. 8.77 times 10 to the minus 7. Okay, so now let's figure out what this S means. S is equal to the concentration of silver ions at equilibrium, right? So if you dissolve silver bromide, you try to dissolve it into water, what you'll find is the concentration of the silver ion would be this value here. So that's in molarity units. And that would also be equal to the concentration of bromide, right? At equilibrium. So it gives you those two quantities, what their concentrations are. But now what we're going to do is we're going to say the following. S is essentially how much of the silver bromide dissolved, meaning stoichiometrically, every time one of these molecules dissolves, if we think of it as a molecule, we get one of these ions and one of these ions, which are S. So in other words, the silver ion concentration is equal to how much of the silver bromide dissolved. So think of it this way. If I draw you a picture of a beaker, and we start, we take our little salt shaker, so have salt in there, and we start sprinkling it in. Some of it's going to dissolve, and some of it's just going to fall down to the bottom as a precipitate. Very little of it actually dissolves. The silver bromide is not all that soluble, so the amount that's dissolved is very small. When we did this calculation, we figured out S. So we figured out how many of the silvers and bromides dissolved, and they were equal to each other. That number is also the number of silver bromides that actually dissolved. Not the amount that we put into the solution, but the amount that actually dissolved. So we call that the molar solubility. So S is called the molar solubility. And it is the moles, again, the moles of the compound that dissolves. So the moles of the silver bromide that dissolved per 1 liter of solution. So if I have 10 liters of solution, 10 times as many moles will dissolve. Okay? The units are moles per liter. So we would say that the molar solubility of silver bromide is 8.7, I'm going to actually round it, 8.8 times 10 to the minus 7 moles per liter. That's the molar solubility, or S. So when you do these problems, S, solve for S, that's going to give you the molar solubility. Okay? Now there's one more calculation I want to show you in terms of this type of problem, and that is to get what's called the solubility, not the molar solubility, but the solubility. We might want to call it mass solubility. So mass solubility is the number of grams of the compound that dissolves into 1 liter of the solution. The number of grams, not the number of moles. Molar solubility is the number of moles per liter. Solubility is in grams per liter. So all we need to do is take our 8.8 times 10 to the minus 7 moles per liter and convert that to grams per liter. And the way we convert the moles of a substance into the number of grams of the substance is we use either the molar mass or the formula mass. So we're going to use the formula mass for silver bromide. So when we go to the periodic table and we look up how much these elements weigh, silver is 107.9 grams per mole, and then bromide is 79.90 grams per mole. So I'm going to go ahead and do that calculation here. 107.9 grams per mole for silver and 79.90 or 79.9 grams per mole for bromine. So that would be 17, and then a 1. So 187.8 grams per mole. So that's, if you want to call it molar mass of silver bromide, that's it. So now what I'm going to do is I'm going to convert this to grams per liter. So the molar mass is 1 mole of silver bromide for every 187.8 grams of silver bromide. And so now the moles of silver bromide will cancel and we'll have grams per liter. So we're just going to multiply by 187.8. So times 187.8, and you get 1.6 times 10 to the minus 4. And this would now be grams per liter. So this is called the solubility or mass solubility. It's the number of grams of the compound that will dissolve into a liter of solution, solubility. Okay? So that's essentially the first type of problem. The second type of problem that we could take a look at is the issue of predicting precipitation reactions. So let me show you what I mean by that. Okay. So the issue here now is whether something will dissolve. Okay? So what we're going to do is we're going to look at, let's take the silver bromide as an example. And we know that the KSP for this one, the KSP for silver bromide is, what is it, 7.7 times, let me actually make sure we've got it, silver bromide, 7.7 times 10 to the minus 13. There we go. And the question is here, suppose that I do the following. Suppose I have a beaker and I take some silver nitrate and I dissolve 1 times 10 to the minus 5 moles of silver nitrate. Now, silver nitrate, because it's a nitrate salt, is very soluble. So as long as you're not putting too much in there, it will all dissolve. And now suppose I do something else. I take sodium bromide, and I'm going to make it I'll make it 1 times 10 to the minus 5 moles also. And I dissolve it. And I ask myself, will there be a reaction? Will the silver ion react with the bromide ion? That's the question. Okay? We know that silver bromide has a pretty small solubility product, 10 to the negative 13. So the question then is, will these two ions react with each other to form a precipitate? If they did, the reaction would be silver ion plus bromide ion to form silver bromide. Okay? So we're not sure whether that's going to happen. So I want to show you a method for figuring out whether they will. First of all, we need to know what the volume is. So just to make things simple, let's say the volume that we're adding is 500 milliliters of silver nitrate solution and 500 milliliters of sodium bromide solution. Right? They're dissolved into water, those two solutions we're adding together. Well, the total volume would be 1,000 milliliters, right? That'd be our total volume. But 1,000 milliliters is the same thing as a liter. Oops, 1.0 liters. So our volume, our total volume, once we add everything together, is going to be 1 liter. Now, the reason I picked those numbers is because that makes the calculation a lot simpler. Because now what I can do is I can say the concentration of silver nitrate that we're dissolving into the water is 1 times 10 to the minus 5 moles divided by 1 liter. So that would be 1 times 10 to the minus 5 moles per liter. And the same is true for the sodium bromide. When we dissolve that, it's 1 times 10 to the minus 5 moles over a liter. And so that would be 1 times 10 to the minus 5 molar. Okay? So there's our concentrations that we're dissolving. Now here's what you do. What you do is you say, okay, in this solution, since both of them dissolved, the concentration of silver is going to be 1.1 times 10 to the minus 5 molar, right? Because this dissolves completely. The solubility guidelines tell us that nitrates will dissolve completely, within reason. So that means all of it's dissolved. So that means the concentration of the silver ion would be the same, 1 times 10 to the minus 5. It's also true that the bromide concentration would be 1 times 10 to the minus 5. They would both be 1 times 10 to the minus 5 molar. Now, here's what we do. We apply our principles of equilibrium, chemical equilibrium. We ask ourselves, how does Q compare to K? In this case, it's KSP. Is Q less than, greater than, or equal to? So how do we calculate Q? We take these concentrations and multiply them together. So that would be 1 times 10 to the minus 5 times 1 times 10 to the minus 5, which would be 1 times 10 to the minus 10. Then we ask ourselves, is Q less than, greater than, or equal to K? Well, K is given up here, 7.7 times 10 to the minus 13. So now we would say that Q is greater than KSP. So that means the reaction goes back towards the silver bromide. Okay? Here's our chemical equilibrium for solubility. AgBr dissolves in water to form Ag plus MBr minus, right? KSP is based on this equation. So if Q is greater than K, that means the reaction goes this way. But look at what happens when it goes that way. What it tells us is the silver ions that are dissolved in here and the bromide ions that are dissolved in here are going to react, going to the left to form AgBr. So we'll see precipitation occur. Okay? So the way you solve this type of problem is you calculate Q. If Q is greater than K, you will precipitate out the solid. The AgBr in this example will precipitate. If Q is less than K, then that means you are below the limit of solubility. There's a small enough a value of the ions that they will not precipitate. So if Q is less than K, the reaction does not result in the formation of a precipitate. And if it's equal to K, then it's right on the cusp. You're right on the solubility limit, and it could or it might not. You may see some formation of solid, but then it might dissolve. It's tricky to get it right at that point. Usually it's either less than or greater than. Very rarely is it equal to. Try the practice problems on these. These are very tricky.